So the last section of chapter 12, 12.7, is going to apply what we've learned about surface area volume, dealing with solids, but now notice it's talking about similar solids. Okay, so we're going to actually apply what we know from past chapters with similar figures, similar polygons, but now we're going to apply it to a three-dimensional. Now, I know you know what similarity means, but similar solids basically means the two solids will have equal ratios of corresponding linear measures, which includes maybe heights or radii or corresponding sides, right? Basically, you're going to compare any two solids, but we wouldn't want to compare like a cylinder to a what?
To a pyramid.
Pyramid, because obviously they're not the same type of solid. Right. So you're going to compare the two types of solids and the corresponding linear measures. The key here is corresponding linear measures are equal ratio. Now, one thing we often will say when they have that corresponding linear measures, that scale factor idea. So just kind of keep that in mind, okay? So what we're going to first, before we actually get to the new idea, is we're going to kind of explore it. Okay. So what I want you guys to do is I actually want you to first answer that first question. Determine, are the following right rectangular prisms similar? All right, so how are we going to determine that? How are we going to determine if they're similar or not? What do you think?
Well, we can definitely look at the side lengths they give us and definitely make sure we match up the corresponding parts. So if we do the small side.
So like 3 is the smallest to
the other small side.
Which is 2. So that would be a 3 to 2, right?
Yes.
And then compare what, 6 to what?
I would say our 4 are two medium pieces.
And that simplifies down to?
Also 3/2.
And then 9 to 6 would also?
It would also be 3/2.
Okay, so it says, are the following right rectangular prisms similar? So I'm going to say yes to that first question, okay? So that first, I'm going to put question 1. So first one is yes, all right? So we found out first if they have corresponding side linear units, basically, that are corresponding. Okay, now here's where we're going to let you kind of do some on your own. It says, if so, all right, we said yes, find the surface areas and volumes of each. Right, so what you got to do is find the surface area of this, find the volume of this. Find the surface area of this, find the volume of this. I know you can do this.
Yeah, you guys know how to do this.
So go ahead and do it. Pause it for a second. Come back and check with us. Okay? So step 2 is find the surface area and volume of each of these solids. All right? So let's try the larger of the two. Okay? So we're going to do the large one first. So how do you find the surface area of a right rectangular prism?
Well, we're going to do 2 base.
The base area plus
the perimeter.
And that's of the base times the height. All right. So because it's a right rectangular prism, does it matter which of the faces is your base?
No, I don't think it does.
Okay. So which one do you want to be the base?
I think my 3 and my 6, just because that looks more like a base.
Okay. To me. So we'll do that one. So to find the area of the base, we're going to do, what, 6 times 3? So that would be 18. And perimeter would be
6 plus 6 plus 3 plus 3, so which also 18.
And then the height would be then what?
The 9.
Okay, so we're going to substitute all of that stuff in. So it'd be 2 times 18 plus 18 times 9. When we get that, we get a total base or surface area of
198.
Okay. So you get the idea. Now, let's find the volume. Volume's a little bit less complicated. So to find the volume of a right rectangular prism, what can we do?
We do the area of the base times the height.
And we already found the area of the base. So basically, we're going to do 18 times
our
9, which is?
It is 162.
Okay. So that's essentially what we're going to do on the other one. Here's the deal. To make this go a little bit faster, because you guys are just checking it with us, well, let's just check what the larger or the smaller one is. Okay, so that's the large one. All right, we're just going to check. So this is the surface area, volume. So for the smaller one, what's the surface area?
Should have gotten 88.
And the volume?
48.
Okay. So, just for checking purposes. Now, the next step says, now let's find the ratio of surface areas and the ratio of volumes.
Okay.
All right, so that's the next step. So if I said find the ratio, it's just comparing two things. So if we're comparing the surface areas, the larger surface area is 198. So this would be the surface area ratio. So we would do 198 to what would be the smaller one?
Our 88.
And if I simplify that down, that becomes
9/4.
All right. And for the volume ratio, we're comparing what to what?
Our volume of our large one, which we got 162, over our small one at 48.
And that simplifies to
27/8.
Okay. Now, the final piece, this is a lot going on in this problem. This is kind of exploring what's happening. The final piece, it says, what do you notice about these ratios? Now, one thing that I didn't write down because I was trying to go through this quickly was when we first asked the first question about if it's similar or not, we had to compare corresponding sides. And we noticed they all simplified down to the side ratio essentially ended up being
3/2.
So I'm giving you a little hint. Okay, take a look at that and then notice the surface area ratio and your volume ratios. Anything you're noticing?
Well, if I look at my surface area ratio, I notice it's just my side ratio squared.
So this is the same thing as 3/2 squared.
Yeah.
Huh.
Yeah.
Okay, kind of sounds like something we've talked about before.
We've kind of learned that.
What about the volume ratio?
Well, it's 3/2 just cubed.
If I cube 3/2, which is cubing 3, which is 27, and cubing 2 gets you 8. And that kind of, in a sense, makes sense. So this whole slide, guys, the whole purpose of this is to explore this only theorem that we're going to have in this section. And the last new idea is all about the fact that, again, these are dealing with similar figures and about the fact of the relationships of some ratios. Okay, so Mrs. Mantle, or Miss Mantle, is going to talk about this theorem.
Okay, so we have similar solids theorem. And it says if two similar solids have a scale factor of A to B, then corresponding areas have a ratio of A squared to B squared, and corresponding volumes have a ratio of A cubed to B cubed.
Okay.
So basically, what it's saying here is just that if we take our side ratio, our scale factor and our side ratio are equal.
Yeah.
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 So if I take my side ratio, which is usually the pieces that they're going to give us, I can just square it to get my area ratio.
And while she's writing that down, I remember talking about this actually in chapter 11 when we talked about similar polygons.
Right.
So when I had that side ratio and I squared it, I always got the area ratio. So that means that would be like surface area. That would mean area of any base, corresponding bases, area of any lateral face, so any areas at all.
So we can use this for a lot of things.
Okay.
Okay, and then we can also say that if we take our side ratio again, and we, let's do ratio there, and we cube it, we can get our volume.
So this is really the new piece.
Yes. But it makes sense. It's very similar to what we already know.
And so, and because volume is talking about cubing things, area is talking about squaring things.
Right.
Excellent.
Okay.
All right, let's actually apply this.
Yes.
So take a look at this first example. Now, kind of a word of advice, guys. I think back to chapter 11, and some of us struggled with the similar polygons because we forgot to like square things when we needed to.
We tried to set up like a scale factor with a proportion with areas.
Exactly.
We can't do that.
So when you're reading the problem, be thinking, okay, are you looking for similar? First of all, guys, we can't use any of this unless you see the word similar, all right? So, or if you already know similar. For example, there are solids, for example, a cube is similar to any other cube.
Right.
Spheres are similar to all other spheres. So unless you already know they're always similar, we better look for that word, okay? So we have two rectangular prisms that are similar with a scale factor of A to B that is 1 to 4, okay? So here's the deal. Knowing that these are two rectangular prisms doesn't really mean a whole lot because we're not really finding, we don't need to know the surface area volume formulas.
Right.
Okay, that's the difference. Because this word's similar, we can bypass a lot of stuff. I want to just real quickly, I didn't think about this until now. Like all of this work right here, all of this stuff right here, if I had given you that the side ratio squared gets you the area ratio, you
Right.
could have just given me that.
Right.
Okay, so this allows you to bypass all that work. So we're going to find the surface area and volume of prism B.
Okay.
Given that the surface area of prism A is 28 feet squared and the volume of prism A is 3 feet cubed. Okay, so let's think about what we know. Right, we have prism A, prism B. We know the scale factor,
Right.
all right, your scale factor of this is 1 to 4. So essentially, which one's the bigger of the two?
B.
Yes.
Prism B.
Now, they give you the surface area and volume of which one?
Prism A.
So I know the surface area is 28, volume is 3.
Yes.
We need to find out these two pieces.
Right.
Okay, so right away, again, I want to keep in mind we're dealing with similar figures, and I'm also dealing with areas and volumes. So we need to remember that scale factor or side ratio, however you want to do it. I'm going to put scale factor, and I'll just do SF for scale factor. That squared gets you the area ratio. And the scale factor cubed gets you the
volume ratio.
All right, so which one do you want to find first? The surface area of prism B or the volume?
Let's go ahead and do surface area.
Okay, so if I'm finding the surface area, I'm going to use that scale factor, all right, which is 1 to 4. But what am I going to do with it?
We're going to have to square it.
Square it. And that will be your surface area ratio, okay? So if I set that equal to my surface area of 28 per prism A to surface area of prism B, all right? Notice I put the A on top because
Right.
it's A to B, all right? What we saw in last chapter, and I think Miss Mansell remembers this, a lot of people, and this is what she was mentioning, a lot of people want to
Yes.
say 1 to 4 is 28 to
Right.
S. Can't do that because you're saying then that the area ratio is the same as the scale factor. The area ratio is the same as the scale factor squared, all right? So we need to make sure we square that. So this is going to be what, 1 to 16 equals 28 to S. So when we go and cross multiply the scale, or this, not scale factor, sorry, the surface area for prism B is what?
448
And this is feet squared. All right. All right, let's find the volume.
Yeah.
Why don't you tell me what I should write down?
Well, we have our scale factor again of 1 over 4, but I'm going to have to cube it this time.
Why is that?
Well, I'm trying to find the volume, and so
Okay.
I need the volume ratio, and I have to cube it. Now I
Okay.
can set it equal to the volume of A that we know,
Which is,
3 over my volume of B I'm trying to find.
and I'm just going to use V. Try not to use X and X because there's two different things.
Right.
Okay, so I like to use S and V because it knows that's what I'm finding. All right, so it'd be 1 over, what, 64 equals 3 over V.
Yep.
So the volume ends up being,
192.
and this is feet cubed because we're talking about volume. All right, so guys, again, solving a portion, you guys are good with that. Just remember, squaring or cubing your scale factor or side ratio, depending on what you're talking about, will give you certain things. Okay? All right.
Okay, so the next example, this one tells us we have 2 cubes that have volumes of 64 meters cubed and 1,000 meters cubed. Ask us to find the scale factor of the cubes.
One thing I'm noticing, and I kind of mentioned this before, we're talking about cubes. I don't see the word similar, but we know that all cubes are similar to each other.
Right.
Because they're a special type of prism. So even though they don't have the word similar, but they do say something about scale factor, and usually when they say scale factor,
Right.
that means similar.
Right. But the past few problems we've been doing, we've had the scale factor.
Okay, so that
But-
makes it different.
Yeah, so this time, what do we have instead?
Well, they're giving you the volumes of the 2 cubes. So I'm thinking, okay, let's write down this. Let's write down our scale factor. Basically, cubed will get you the volume ratio.
Right.
Let's write that down so I can kind of remember this. So really, essentially, since they're giving you the 2 volumes, we're going to have to kind of work backwards.
Right.
So if I
I'm
have
starting
my...
with this now. I'm trying to get here.
So I have the volume, let's say 64 over 1,000. Let's just put it in that order. I'm thinking that what we probably want to do is cube root that because I'm going to go backwards. To undo a cube, we're going to take the cube root.
So I'm going to have to cube root both of these.
All right, and when you take the cube root of 64, you get 4. And when you take the cube root of 1,000, you get 10.
Okay.
And then I want us to make sure that's simplified.
Right.
So that would be 2 over 5.
Okay.
Now, something you also could do is 64 over 1,000 could have been simplified first.
Right.
All right? If you think about it, if I put 64 over 1,000 in my calculator, it simplifies to 8 over 125 once you write that down. And let's see if I get the same thing. If I go ahead and cube root the 8 and cube root the 125, I still get 2 over 5.
Right.
So it's either simplifying beginning or simplifying at the end. I personally sometimes like simplifying before, so then that way
it's a little easier to think of.
it's less smaller values to work with.
Right, absolutely.
All right, let's look at the next one. And I want you guys to try this one on your own. Okay, so hit pause and then check it with us. All right, so what does it say?
We are dealing with two similar cones that they tell us they're similar. I noticed
Yes,
that right away.
right away,
We
good.
know they're similar. Okay, and they have a surface areas of 384 pi feet squared and 216 pi feet squared.
And they're asking us to find.
The scale factor.
Okay, so I love that Miss Bates will notice it said similar because not all cones are similar. But knowing that they're similar and I see the word scale factor, we know we're dealing with similarity.
Right.
And this time, they're giving you the
surface areas.
So right away, I want you to remember, okay, so my scale factor, and I'm just going to abbreviate here, squared gets you your surface area, or the area ratio. I'll just put area ratio, not just surface area ratio. So I'm, again, really stressing that because we keep forgetting that, or we kept forgetting that back in Chapter 11. So we're going to kind of have to work backwards in a sense, kind of like the last one, right?
Yeah.
So what do you want me to write down?
Well, we know they're giving us our surface area. So
Okay.
we know our area ratio.
Okay.
And we can set it up of 384 over
384
for pi.
pi.
Don't forget that pi.
Yes.
And 216 pi.
And that's your area ratio in a sense. Now, here's the deal. The last one, what we did was to get because we were given the volume ratio, to work backwards, we took the cube root. Are we going to do that on this one?
Well, no. Because
What are we going to have to do?
we're going to have to do square root.
Now, here's the deal. If I take the square root of 384 pi, it's not real convenient.
No.
So what would be a good suggestion to do first?
Well, I know I can just cancel my pi's.
Okay, so in other words, kind of simplify this down first. So let's simplify. Let me make a little note. Simplify this ratio first. Because think about it, guys. Ratios should be simplified anyway. So if I cancel out the pi's, that's going to go away. But I'm still 384 and 216. And they're not perfect squares.
No.
So if we take the square root, we're going to have to simplify radicals. And I don't want to do that. Okay, so there's got to be a way. And I see that these can be simplified down.
Absolutely.
384 over 216 simplifies to
16 over 9.
so much easier to work with, right? So what are we going to do with that?
Well, we're going to square root them now. And it's a lot easier. There's 16 and 9. I know it's 4 over 3.
So much easier, exactly. So kind of word of advice, this last one, we didn't kind of stress that in the beginning because it didn't need to be. This one, you could do this. We could take the square root of 384 and the square root of 216, but if you type that in your calculator, it's a decimal, so we would have to leave it in radical form and then kind of mess with that. Why do that? Let's simplify, then take the square root. Okay? All right.
Okay, Ms. Palermo, what is going on in this example?
All right, so it says we have two fish tanks that are similar. So again, keyword there, similar figures.
Right away.
All right, it says one of the fish tanks holds 5 gallons and the other holds 12 gallons. Now, right away I'm thinking, what is 5 gallons really involving or 12 gallons involving?
Right. And it's talking about holding it. I think that's probably volume.
Yeah. So if you think about a fish tank, what's inside of it, we're talking about volume. So I love that you write that down. So the 5 gallons and the 12 gallons involves the volume of that fish tank. And we don't know what kind of fish tanks they are.
Right.
All right. Most fish tanks are probably rectangular prisms, but you have those more circular ones. All right. It says if the length of the 5-gallon tank is 14 inches. what is the length of the 12-gallon tank?
Okay.
So let's kind of jot some ideas down.
Right.
So we have a 5-gallon tank with a length of 14 inches. So 5 gallons has a length of 14 inches.
Yes.
And then the 12-gallon tank, we don't know the
Yeah.
So we'll just put 12-gallon and we'll put length equals question mark.
That's what we're trying to find. Okay. Well, what information do they give us that
Okay.
we can use?
Well, we can use the fact that they give us the volume and they give us these are similar. So I could probably set a proportion.
Okay.
But the fact is, again, we're given volume and we're dealing with length. So I'm probably going to have to keep that in mind. So I know the volume ratio
right.
is equal to my like side ratio squared
Right.
or cubed.
So I can have my volume ratio, but really we're trying to do side ratio. So what do I have to do?
We have to cube the side ratio.
Okay. So I'm going to have to keep that in mind while I'm doing this problem.
Okay, so my volume ratio is going to be comparing the two volumes. So I have a 5-gallon
Okay.
to a 12-gallon. And that's going to equal my side ratio cubed. So in the 5-gallon, there's a 14-inch
Right.
length.
And I want to make sure I match those up.
So that'd be on the top.
Uh-huh.
Over my length of the other one. Now, if you leave it like that,
I'm going to get wrong.
I'm going to get it wrong because you're saying volume ratio is the side ratio.
Right.
But it's the side ratio cubed. So I'm going to cube that whole thing. Exactly.
Now, Ms. Palermo, why didn't you cube root your
You,
volume ratio?
well, you could.
Yeah.
You could. I like that question. Because if you do that, it still would get you the same result, but then you're dealing with
Some not pretty numbers.
decimal kind of stuff. Okay, I like this idea.
Either way would work, but the cubing will be a little bit easier and cleaner.
Okay, so let's go ahead and start solving this. So
Okay.
on the right side or on the left side, I'm just going to keep 5 over 12.
Uh-huh.
And then I'm cubing the 14. That gets you 2,744. And then over, I got to cube the length too.
Right.
Don't forget that.
Right.
Now I'm going to do a little cross multiplying.
So I get 5 L cubed.
And then when I multiply 12 times that 2,744, I get 32,928.
Okay.
And then I'm going to divide by 5.
Okay.
All right. So then I'm going to get my
Okay,
L
over
cubed.
here.
That's perfect. L cubed is 6,585.6. Now, I want the length.
Right.
So to get rid of a cubed, what do I got to do?
Cube root.
So I'm going to, again, I got to make sure I cube root it. So
Not
here's,
just square root.
when I put this in my calculator, I'm going to put the cube root first. So I'm going to hit that 3-second caret button. And then I'm going to do the answer recall. So I don't have to type it in again. Now you
Right.
could because that was exact.
That one's not too bad.
Now this will be an approximate. So it's around
Yeah.
18.74. And this is in inches, just inches.
Right. Because it's not cubed anymore. We cube rooted.
And that is it.